Hi there and welcome. This is the third video in chapter 13 of the DB2 course, and it's now time to explore the details of the on-demand query plan evaluation in PostgreSQL, the so-called Volcano Iterator style on-demand pipelining. What's behind that is a very simple idea, a very simple protocol that all of the operators that we support in our database system have to implement. It's a protocol or an API, an interface that all operators commonly support. And when I'm talking about operators here, I'm talking about nested loop join, for example, or group aggregate, or a particular sort implementation. So all of these operators that can act as plan operators in our system will implement the same Volcano Iterator API. All right, and with the help of this API, we implement this demand-driven query evaluation. The API is really simple. It only consists of three operators, of three functions that have to be implemented by each of these operators. The open, next, and close function call. In open, every operator will be requested to initialize itself, to set up its internal data structures, if there are any, and to prepare for the subsequent evaluation. It will then forward this open request to all of its upstream subplans. So let's imagine that we are talking about a binary operator like a nested loop join. If the nested loop join operator receives the open request, it will of course set up itself, and we will see on the next slides how a nested loop join might prepare itself for evaluation, and then it will forward the open call into its left and the right hand side join lag, so that these subplans indeed can also open and prepare themselves. As a consequence, we only have to send the open request once to the plan root, which will then forward the open to its subplan, which will then further forward it to its subplan until we reach the leaves. So a single open call to the plan root will be able to initialize the entire plan. All right. Next, we'll ask the operator to produce the single next row, the next result row that it can deliver. Probably that means that this particular operator will forward the next call down to its subplan because it needs input from the subplans to produce one output row. All right. So again, posting a next call to the plan root will probably lead to postings of next calls downwards the plan towards the leaves until the leaves have to respond to next. And well, you can imagine what a sequential scan will do on the next call. It will just forward its read pointer into the heap file of the relation that is being scanned and, well, return the next row in this particular sequential scan. Okay, so this is what next is performing. It only delivers the next output row. Okay, if this is possible at all. Maybe a sequential scan had already exhausted its scan of its underlying heap file. Well, then we have to return a null indicator. Null indicates to the calling plan, to the parent operator, that no more results are being or can be produced by this particular subplan. Then the parent operator will react according to this situation. It will either also pass null to its calling parent operator, or, well, it may act differently, as we will see in the nested loop join case. All right, so we will either deliver the next output row on next, or we will deliver null to indicate that the delivery of rows is complete. Right, and then there is the counterpart to open. It's the close API call, which will ask the operator to release its internal state. Well, deallocate any memory that has been allocated. Maybe we are talking about a blocking operator that needs some internal memory buffer to hold its intermediate result. On a close call, release and deallocate such internal resources to clean up after yourselves. Of course, we would also forward the close call to all our sub-plans so that these sub-plans also get the chance to deallocate their intermediate temporary resources. All right, and then following this Volcano-style protocol would simply mean for an operator to react to an initializing open call. Then that operator will probably receive many next calls, maybe none, but probably a whole sequence of next calls until the operator is being signaled that the overall plan evaluation should end, and it will receive a close call to clean up after itself. Now there is this overarching and closing plus here, and that should indicate that such open, next, close call sequences might occur multiple times for an operator during a single plan evaluation. Imagine that you are on the inner leg of a nested loop join. The inner leg of a nested loop join will be required to scan the underlying relation many times. For each outer row, well, the inner plan has to be evaluated in the case of a nested loop join. And so we can imagine that the inner leg will probably see open, next, close calls once the first outer row is considered by the nested loop join, and it will receive a very similar sequence of open, next, close calls when the second outer row is considered, and so on. All right, but that would be the sequence of API calls that you can expect. Open, multiple next, close, and the entire thing may be repeated. Okay, right. So, next only delivers the next output row. Of course, the database system is interested in producing the entire query result. And as such, it uses a driver routine, the eval routine, the evaluation routine, that would receive the plan for one particular query queue. So behind this parameter queue here, we would assume that we find the plan tree for this particular query. All right, so to fully evaluate this query, the database system would follow the following routine. It would, of course, open the root, which is just this parameter queue. It would open the root of the particular plan. And, of course, the whole plan would initialize itself because open is forwarded deep into the plan. Then we would request the first tuple T that this plan can deliver. If this tuple T is not null, if the plan indicates that indeed one row has been returned, this row is bound to T, then of course we would emit this particular row and print it on the pSQL prompt or deliver it to the calling application. Okay, then we would consider to evaluate the next output row. Okay, so the plan would be requested to deliver the next output row. Everything is happening on demand here, right? So if we don't request that, the plan queue won't deliver anything else. We demand the next output row. If that is not a null row, we would emit it. If it's a null row, then we have seen all the rows that the plan can produce, and we'll then close the plan to properly clean up after ourselves and give all the operators in the plan the chance to deallocate their resources. All right, so this would be a loop that drives the Volcano operator protocol at the very top of the plan. Everything else is derived from this particular sequence of open, next, close calls. All the other dynamicity inside the plan derives from this demanding of the next query row or result row at the plan root. Okay. Well, this close call is something that we might also use if somebody attempts to cancel query evaluation. So if you would have some logic inside this loop here that checks for extraordinary conditions, like, for example, canceling the particular query evaluation, to cancel the evaluation of a plan means to finally call close on the root, just to make sure that all the resources in the plan are being removed and freed again. Okay, so if this is the very simple Volcano Iterator protocol, then let's see how these open next close calls are being forwarded inside such a plan tree. And to demonstrate that, I've just I brought this this sample plan tree with me. It's a plan tree that has its root here at the right hand side and its two leaves at the left hand side here. So this must be some binary operator, probably a nested loop join operator or some other binary operator that is being placed in the plan. We would start in this particular configuration. Q is the root of the plan. We would start the whole query relation with an open call at this particular root. Well, the root can probably do nothing at this particular point. It will forward the open call to its upstream plan, and where the open call would then reach this particular operator, which again will forward the open call further down the plan until it reaches this binary operator, which would then prompt that operator to forward the open call into its both legs, where it will then hit these leaves here. Probably these leaves are index scans or sequential scans. They would initialize their scans. They would open the heap file. They would position their read pointers at the very beginning, at the first page of the read file, to prepare themselves for query evaluation. All right. Right. Well, the same, of course, would happen with close. We would enter with a close call here at the root of the plan, and it would trickle down the entire plan until these close calls reach these leaves of the plan, where we would probably close files or deallocate other resources. Okay, so let's have a closer look. Let's have a closer look at the Volcano API implementation, at the implementation of the open, next, and closed functions for such a binary operator here, for the nested loop join, for example. Okay. So implementing the Volcano API Iterator model requests to implement three functions: open, close, and next. Open and close are very simple in the case of nested loop join, and they are very simple for most of the operators that you will encounter. So they fit on a single slide here. We've got open here for the nested loop join operator, and we've got close here for the nested loop join operator. Okay, these are the parameters for this nested loop join operator. It will have two upstream plans, the outer and the inner plan. Well, this is a nested loop join. One of the legs will be the outer, the other will be the inner leg. And well, then there is the join predicate that we have to evaluate at this particular point. Okay, so well, if we have to open ourselves, if we have to open a nested loop join, well, we will open the outer and the inner, the legs, the subordinate legs inside the plan themselves. So we are forwarding the outer call to the left and to the right here. Well, this could even be done in parallel. So there is no interdependencies between these subplans. So if there are the CPU resources available, then we could open these plans in parallel even. All right. Then there is only some very minor bookkeeping to be done inside our nested loop join operator. We only need very limited internal state for this nested loop join operator. It's just a Boolean flag that will indicate to, in particular to the next routine, whether it is time to request a new row from the outer leg. Okay, so in the very beginning, indeed, a nested loop join would start with requesting the first row from the outer leg. So we will set this Boolean flag to true at this particular point, prompting our next function that we will see on the upcoming slide to indeed request the next row, in this case the first row from the outer leg. All right, and then there is a very minimal state that we have to keep inside our nested loop join operator. It's just a state that can keep one single row, one single outer row. Okay, and well, currently we don't have that outer row available, so we set that inner state, this variable O that will hold the outer row, to null here. All right, and that's all there is to be said for the open implementation of nested loop join. Super simple and very limited local state that we have to maintain. So it's even simpler for the close implementation of our nested loop join here. We will simply forward the close calls to our outer and inner legs here and have them clean up after themselves. There's only these two very minor bits of state that we have allocated statically. Let's assume that this is allocated statically inside our routine. So there is even no deallocation of dynamic memory resources necessary in the case of nested loop join. Okay, so how about the next routine? How about the next routine for nested loop join? Well, it's also very simple and it fits on to a single slide. All right, so how about the implementation of next for a nested loop join? Again, we've got the outer, inner, and the join predicate as parameters here. What you will see is that the top level of this nested loop join indeed is an endless loop. All right, so let forever denote an endless loop that will actually on itself will never terminate. So this suggests that nested loop join next does a whole lot of work, maybe all of the work at this particular point. But this is indeed not the case. You will see that we return from this nested loop join in due course, and we will make sure that only one single row is delivered for each invocation of nested loop join next. Well, maybe even no row is delivered in the case where we have to respond with null. Okay, so well, we would enter the control flow here at this forever loop and then check our Boolean flag if it's required to read a new row from the outer leg. Okay, so in the very beginning, if you recall, the need new outer Boolean flag has been set to true by our open routine. So the first time we enter next, we will indeed need a new outer row from the leg, and that's what we do. We request the next row O from our outer leg, and this will respond with a single row. Well, maybe it will respond with a null row. In this case, there is no further join results that we can produce. If one of the inputs to our join operation delivers no rows, well, then as a join operator, we can deliver nothing, and we would indeed immediately return with null here. Okay, so that would be the first point where we end and leave this endless loop. All right, if we reach this particular line, then we've got a new outer row. Okay, so that will be the outer row for which we will now perform the scan of the inner. So in the next few instances of our next call, we won't need a new outer row, and we indicate this by setting the Boolean flag to false. Now it would be time to prepare the inner, relation for a new scan from the very beginning of the inner leg. And we perform that by closing the inner and then reopening immediately. Closing the inner will deallocate any resources of previous inner scans, will then reopen the scan. The read pointer will be set to the very beginning of the heap file. So at this point, if we reach this point, the inner has been prepared to rescan its entire row contents. Okay, and that's what we need. We've got one outer row. It's called O here. We will get the next inner row. Maybe it's the first inner row if we have just resetted the inner. We will get the next inner row, call that I. Well, if the inner delivers no further rows, then the inner may be exhausted, and it's time to check for the next outer row. And this will be indicated by this Boolean flag again. All right. Well, if we indeed got an inner row successfully, well, then it's at last it's time to evaluate the join predicate. If you've got a join pair, then this join pair will be returned, and our job is done at this particular point. We have produced one row. This is all what next is supposed to do. We have produced the row, and we can successfully return. Otherwise, maybe this OI combination has not satisfy the join predicate, well, then we are on the lookout for the next successful join pair that we can form. It's our task to deliver one output row or to answer with null. So we have to return to the top of the loop here and then, well, request either the next outer row, probably we won't need a new outer row, or request the next inner row, next inner row, and then check for that particular inner row whether the join predicate is fulfilled. Maybe it's fulfilled, then we can return. Otherwise, it's not fulfilled, and we have to return to the top of the loop here. All right. I invite you to replay the logic of this loop for different situations where the outer is exhausted, where the inner is exhausted, where the join predicate theta is satisfied, is not satisfied. You should see that that the flow of control through this loop will always lead you to either return a single successfully formed join pair or to return null in the case where actually all the inputs have been exhaustively consumed. Okay, right, so this is a somewhat unusual style of expressing nested loop join semantics or the implementation. I hope you still recognize the basic idea of nested loop join in this routine. It's formulated in a style of a so-called coroutine. Well, we won't dive into the details of coroutines here in this particular course, but maybe you want to use that as a keyword to dive deeper into the implementation of routines that only perform part of their duty on every call and then resume their operation on the next call. All right. Right, so we have visualized how open is being forwarded in the plan tree on the previous slide. Let's do the same for the forwarding of a next call deep down into the plan. Okay, and that would be this particular slide. So this is a rather packed slide, but please read that slide in the order of these numbers here. They are different time steps that represent the state of the plan at different points in time. Okay, so we really start out with the evaluation of this particular plan when we enter the plan route with the next call. Okay, the next call would be forwarded by the plan route to this particular operator, which is a group operator as indicated over here. Okay, that group operator cannot do anything without requesting input from its upstream subordinate plan. So it does just that by forwarding the next call downwards to this particular operator. This is a nested loop join operator. Okay, so this is a nested loop join implemented in just the style that we've described on slide 14. Okay. So that particular operator, if you flip back to the pseudocode, it will receive a next call and will forward the next call to its outer leg, because need new outer at this particular point will be true. So forwarding that call to the outer leg will be a sequential scan, and that sequential scan will finally produce one row that can return. This is the row that is being returned. So you see our sequential scan reads a two-column relation with column values 1 and capital A here. This is being returned and being passed to our nested loop join at this particular point. The nested loop join will receive this row and it will save it into variable O. So this becomes part of the intermediate state of our nested loop join. This is actually the only state, besides the Boolean flag, this is the only state that the nested loop join has to keep internally. That one particular row that has been delivered by the outer. Now it would be time to request the next row from the inner. So we forward the next call to the inner. The inner will respond with one particular row. This is the row returned by the inner. It will be passed back to the nested loop join operation. And now at the very bottom of that nested loop join routine, we have all the ingredients available to evaluate the join predicate, theta. And in this case, it's just a simple equi-join that would compare the A value in the outer row and the A value in the inner row. Both are 1, so the join predicate would be fulfilled. we would return from the nested loop join implementation of next and pass the joined row. This is the joined row. We would pass the joined row up to our downstream plan, which would then be received by the group by operator. Well, the group by operator would do its thing and build its internal state up, and its internal state will be more substantial. It will be indeed be a hash table keyed on these A values, and well, the hash table would also create all the necessary data to compute aggregates. And in this case, it's just the count aggregate, so we would simply maintain a counter here. All right. Well, as we discussed already, such an aggregate operator is a blocking operator. This operator at this point in time cannot return to the root here. We can only return from this aggregate operator once we have seen all the inputs and once we have actually constructed all the groups and maintained all the aggregates. So the next thing that will happen is not to parse anything back to the root here, but we will demand the next input from our subordinate plan, and we will perform the next call down to this join operator. And this is exactly what happens. All right, so the root operator still has to wait. This is a blocking operator. It requires the next input from the join. The join will see that it does not need a new outer. Here is a new outer that has been saved in the state variable. The Boolean flag is false. So we would immediately forward the next call to the inner. The inner would respond with a row. The row would be passed back to the join operator. Now is the time to evaluate the join predicate. The join predicate indeed is not satisfied. Okay, so well, what the join operator will now do is request the next inner input tuple. Okay, so we will hold on to the outer and we will request the next inner input tuple. And the next will lead the sequential scan at the leaves here to return the next inner row. Here's the next inner row. It will be returned to the join operator. The join operator will see that the join predicate is not satisfied, so that inner row cannot lead to a new join pair. So all that's left to do is indeed request the next inner row from the inner leg. Okay, so another next call to the inner leg here. At this particular point, the inner leg is really exhausted and it cannot deliver anything else, so it will respond with a null call here. All right, so let's continue on the next slide. Returning null to this join operator will prompt that operator to set the need new outer flag to true again. So the inner is exhausted. It's now time to switch to the next outer tuple. All right, so that's what we are going to do. We will request the next outer tuple. This will be produced. It will be passed back to the nested loop join implementation, where it will be held as a new binding for our inner state variable, for the state variable O. At that point, we will request the next row. At this point, we would request the inner to reset itself with close and open calls, and then request the next row with from the inner to continue with the entire computation. I think it would be best if this particular annotation here would say close, open, next. I think this would be a better annotation here, a more complete annotation at this particular point. And I think I will alter the slide before I upload it for you to print. Okay, so that would be the routing and the dynamics that is created by passing a next call from the root down into the plan. You see that the evaluation of all the subordinate plans and all the coordination and maybe re-evaluation of the inner plans happens automatically. Okay, I think this is well, quite an elegant approach to the implementation of plan evaluation, and well, it leads to very interesting and sometimes very beneficial on-demand evaluation behavior, as we have seen in our 100, 100, 100 example in the last video. I can only urge you to think about how you would implement other plant operators. For example, the following here, how you would implement other plant operators in this Volcano Iterator Model style, implementing the API of open, next, close for all of these operator instances. I think some of these are very simple, some of these are more sophisticated, but I think all of them will be really quite eye-opening. Okay, so much for our discussion of the Volcano API. You can very nicely see the effects of the Volcano API if you have a closer look at plan evaluation inside PostgreSQL. In the next video, I would like to show you one such way that allows you to really measure the time that it needs to produce the next output row in a plan only. So not to deliver the entire result, but only request the next row. And that gives you some insight into the internals and the implementation of these operators in PostgreSQL. It's quite interesting. All right, so much for this video. This is the Volcano on-demand plan evaluation in PostgreSQL. Next video, some more details on that, and I think we can then already call it a day regarding chapter 13. Until then, take care, bye-bye.